This video is about Chapter 8 of our course in Linear Systems Theory, whose title is Functions of a Square Matrix. We begin this chapter with a short review of analytic functions, which should be known from undergraduate complex analysis. So let alpha k be a sequence of complex numbers and S be a complex variable. Now consider the infinite power series shown here, where we multiply the elements of the sequence alpha with increasing powers of S, and the infinite sum is of course defined as the limit of a finite sum, so where the index k goes from 0 to n, and then we let this n up here go to infinity. An important question is of course, when does this limit exist, depending on the sequence alpha k? There is an important result on this, stated in fact 8.1. It's one of the central elements of a basic course in complex analysis, and therefore we will not repeat the proof here. However, we will use the result. And this result says that for any given sequence alpha k, there exists a convergence radius r, which is a positive real number, such that the power series of equation 7, A, converges for all complex variables s with absolute value of s is less than r, and B diverges for all complex variables s whose absolute value is greater than r. It's easy to visualize fact 8.1 with a little illustration in the complex plane. So let any sequence alpha k be given, then the infinite power series of equation 7 has the following convergence properties. There exists a convergence radius r, which of course depends on the sequence alpha k, such that inside a disk with the radius r, we have convergence of the power series for every s inside the disk, and we have divergence of the power series for every s outside of the disk. In fact, what happens exactly on the disk is quite complicated and it cannot be stated in general, which means that the power series might converge for some of the values on this disk and it might diverge for others. So fact 8.1 actually doesn't make any statement about what's happening on the boundary of the disk. Now suppose that for a given sequence alpha k, r is the corresponding convergence radius of the infinite series. Then the infinite power series defines a complex function whose domain is the interior of the disk with radius r, so basically the convergence region of the power series, and whose codomain is C. In the following, the region of convergence, which is an open disk centered at the origin and which has the convergence radius r, is denoted with the D, and here we have the center, which is the origin, and the radius r. Note that the statement of fact 8.1 with the convergence radius r implies the extreme cases where the convergence radius r might be equal to 0, which means that the infinite power series converges for no value of s, and the other extreme case is where r equals to infinity, which means that the infinite power series converges for all values of s. Now, definition 8.2 states that a function that's defined in the way we have just described, so by a convergent power series on a disk with radius r, is said to be analytic on this disk. Analytic functions in complex analysis are also often called holomorphic functions. So analytic and holomorphic can be regarded as synonyms. For this class of analytic or holomorphic functions, we have the important Theorem 8.2, which is also known as Taylor's theorem, and it's about Taylor series, which certainly any one of us has seen before, or to be more precise in this context, about Maclaurin's series. And the statement of Taylor's theorem goes as follows. Let f be an analytic function which maps from its convergence disk into the set of complex numbers. Then, first of all, f is an infinitely differentiable function on its domain, meaning that arbitrary derivatives of f, denoted by fn, for any order n in the set of natural numbers exist. Moreover, f can be expressed at any point of its domain S by a so-called Maclaurin series, which reads as follows: f of 0 plus 1 over 1 factorial times the first derivative of f at 0 times s plus 1 over 2 factorial times the second derivative of f at 0 times s squared, and so on, which equals to this infinite power series. Corresponding power series formulas, of course, also hold for all derivatives of f. So, for instance, this power series representation for the first derivative of f, and this one for the second derivative of f, and so on. Two additional remarks about Theorem 8.3. The first one is about the difference between a Taylor series, which might be more well known to most of you, and a Maclaurin series. It's actually easy to explain based on the general formula of a Taylor series. For the Taylor series, the function value f of s is given as an infinite sum from k equals 0 to infinity of 1 over k factorial times the kth derivative of f at s naught times s minus s naught in brackets to the power k, where s naught is an arbitrary value in the complex plane C. The Maclaurin series, on the other hand, is just a special case of the Taylor series, where the center point s naught has to be chosen as the origin, so s naught equals to 0. The second remark is about the difference between an analytic or holomorphic function and an infinitely differentiable function. It's a common misconception that these two classes of functions are actually the same, and hence some people believe that any function which is infinitely differentiable also has corresponding Taylor series or a corresponding Maclaurin series. But this is not true. In fact, this little illustration here shows that the class of infinitely differentiable functions is much larger than the class of analytic functions. So clearly, every analytic function is infinitely differentiable according to Theorem 8.3, but the converse is not true. So let's look at an example. F of s equals to e to the minus 1 over s squared. In fact, when we calculate all derivatives of this function f, this yields that the first derivative at 0 equals to the second derivative at 0 equals to the third derivative at 0, and so on, and all of them equal to 0. And you should check this fact for yourself by calculating the first few derivatives of this function. By the formula for the Maclaurin series in Theorem 8.3, this fact that all of the derivatives are 0 would imply that the function has to be equal to the 0 function, which is obviously not true because e to the minus 1 over s squared is not the zero function. Therefore, we can conclude that this function here cannot be analytic, even though it is in fact infinitely differentiable. If you did not feel familiar with this review of analytic functions on the previous two slides, there's no need to worry. Even if you did not have any complex analysis as part of your undergraduate curriculum, you should be able to follow the rest of this chapter without much problems. You can just take the definitions and statements in the review as given, and at any point in the future, go back and study the details of complex analysis and fill in the proofs and background material that's missing right now. So all we're going to use in this course are the results stated in the review. And specifically, we're going to use these results to define functions of a square matrix. And this basic idea is explained on the next two slides. So consider a square matrix A in C n by n. Since A is square, we can multiply A with itself, and hence we can define A squared as A times A cubed as A times A times A, and so on. In fact, we can define arbitrary powers of A, like A to the n, by just multiplying A with itself n times. In the next step, since we have defined arbitrary powers of a matrix, we can also define what's called a matrix polynomial. For this, consider an ordinary polynomial that we call P of s, where gamma k represent the complex coefficients and s is the scalar variable of the complex polynomial P of s. Then we can define a corresponding matrix polynomial called P of A, where we just replace the powers of the scalar variable s with the powers of the matrix A. This is really not very complicated. So for example, take the scalar polynomial P of s to be equal to s to the 5 plus 2s to the 3 plus 5s squared plus 7. Then the corresponding matrix polynomial is simply P of A, which is equal to a to the 5, which is defined as a times a times a times a times a, plus 2 times a cubed, where a cubed is defined as a times a times a, plus 5 times a squared, where a squared is a times a, plus 7 times the identity matrix. Observe that no matter which scalar polynomial we choose here, the corresponding matrix polynomial P of A will always represent an n by n matrix. This notion of matrix polynomials can now be generalized to arbitrary analytic functions of a square matrix, as shown in fact 8.4. So consider any scalar analytic function f, which, as we have seen, maps from some open disk in the complex plane into the complex numbers, and which has a corresponding Maclaurin series for some sequence of complex numbers gamma k. Suppose that the convergence radius r of the Maclaurin series of the scalar function is greater than the absolute value of all eigenvalues of the matrix A. And we shall see in just a moment why we need this particular condition. Then the infinite series f of A, which equals to this infinite matrix polynomial, converges, and moreover f is a function that maps from the set of n by n matrices into the set of n by n matrices is well defined as a matrix function. So just to clarify, on the previous slide we have defined a finite matrix polynomial which maps any square matrix A to another square matrix P of A. In fact, 8.4, we're now considering infinite polynomials of matrices, which obviously still map from an n by n matrix to an n by n matrix, but where we now need to be concerned about the convergence. So when does this infinite sum of matrices converge? And the answer is given that if the convergence radius r of the corresponding scalar polynomial is greater than the absolute value of all eigenvalues of A, then we have convergence and we can consider this infinite polynomial as a function of a square matrix. For an illustrating example, let's consider the exponential function. As it is well known, in the scalar case, the exponential function of a complex variable s is defined by this Maclaurin series, which every one of us has seen before. It's also well known that this Maclaurin series converges for all s in the complex plane, which means that the convergence radius of this scalar Maclaurin series is infinity. Of course, this is convenient with respect to the convergence condition for the corresponding matrix function, because any matrix A will satisfy that all of its eigenvalues are in absolute value less than the convergence radius if the convergence radius is equal to infinity. Therefore, for any arbitrary n by n matrix A, we can define the corresponding matrix function to the scalar exponential function as the same infinite polynomial as in the scalar case, where we now have just replaced the scalar variable s with the matrix A. And for the scalar exponential function, the corresponding matrix function is called the matrix exponential function, or simply the matrix exponential. In fact, this matrix exponential plays a dominant role in the theory of linear systems, and we will encounter it many times in the rest of this course. Before we go on with using matrix exponentials and seeing how we can actually compute them, we first state a few helpful properties of general matrix functions in lemma 8.5. So let A and B be two arbitrary square matrices, and f of s and g of s be two arbitrary scalar functions. Assuming that the respective matrix functions in the following statements are well defined, we have the following results. A, f of A times the matrix A is equal to A times f of A. B, if A and B commute, so B times A equals to A times B, then B times f of A is equal to f of A times B. C, f of a similarity transformation of A, so T here is an invertible transformation matrix, is equal to the similarity transformation of f of A. D, f of A transpose is equal to f of A transpose. E, if h of s equals to f of s times g of s, then also h of A equals to f of A times g of A and equals to g of A times f of A. And finally f, the function f of a block diagonal matrix whose diagonal blocks are A and B equals to the block diagonal matrix whose diagonal blocks are f of A and f of B. Let's go quickly over the proof of lemma 8.5, as some parts are not very interesting. In fact, for all parts of the proof, we shall use the definition of f as an infinite series, meaning that there exists a sequence of scalars gamma k such that f of a can be expressed as the infinite sum from k equals 0 to infinity of gamma k times a to the k. For part A, note that we can write a times f of a as a times the infinite series, and now we can pull this a into the sum, which means that a multiplies each of the existing terms gamma k a to the k, which results in gamma k times a to the k plus 1. And then we can again pull out a factor of a from each of these terms, this time to the right, and we get to this expression, which is of course nothing but f of a times a. The proof of part B is similar to part A, and therefore we skip the details here. Only one remark, that at this point in the proof we need to use the assumption that A and B commute. For part C, first of all, observe that for any natural number k, it holds that the matrix T inverse AT to the power k can be written like this, where we have a total number of k of these factors, where we can of course remove all of these brackets between the factors, and then the multiplication of t with T inverse gives identity in between any two matrices A. So we can do this k minus 1 times, and what we end up with is T inverse A to the k t. Now we can use this to establish our result. F of T inverse AT is by definition equal to the sum of k from 0 to infinity of, in brackets, T inverse AT to the power k, which by our previous result is equal to the sum of k from 0 to infinity of T inverse A to the power k t, where we can now take the T inverse out to the left and the t out to the right, and what we get is this expression, which is exactly equal to T inverse f of a t. Part D is again very uninteresting, therefore it's just stated here for completeness. Note, however, that the very same argument also works for the adjoint instead of the transpose. For part C, in analogy to f of a, we first express g of a as an infinite series for a sequence of complex numbers beta k. Then the function h of a, defined as the sum of k from 0 to infinity alpha k a to the k, where the complex numbers alpha k are defined as shown here. So alpha 0 equals to beta 0 times gamma 0. Alpha 1 is defined as beta 1 gamma 0 plus beta 0 gamma 1. Alpha 2 is defined as beta 2 gamma 0 plus beta 1 gamma 1 plus beta 0 gamma 2. So for any alpha k, we always sum up the products of betas and gammas such that the sum of the two indices is equal to k. In other words, the general formula for alpha k is given by the sum of I from 0 to k of the products of beta k minus I times gamma I. Now observe that the function h of a, defined like this, satisfies that h of a equals to f of a times g of a, but also equals to g of a times f of a, which can be verified by comparing the corresponding coefficients of the powers of A in the multiplication of the two sums. Finally, for part F, observe that for any natural number k, we have that a block diagonal matrix to the power k is equal to taking the block diagonal elements to the power k. This can be easily verified by induction, so multiplying the block diagonal matrix with itself, and then with itself 3 times, with itself 4 times, and so on. Therefore, f of this block diagonal matrix, which is defined by this sum, can also be written as the sum where we now take the kth power of the block diagonal elements instead, where we can now pull the scalars and the summation inside of the matrix, and what we get is exactly what we want, namely a block diagonal matrix whose blocks are given by f of A and f of B. So this completes the proof of lemma 8.5. Now that we have defined matrix functions, and after we've looked at some useful properties, we will now turn our attention on how to actually compute matrix functions for a given matrix. Because obviously, the infinite series that defines the matrix function is not a practical way to actually compute the matrix function. Let's begin with case 1, where the matrix A that we want to compute a function of is simple, which means that according to theorem 7.7, there exist two matrices T and lambda such that lambda is equal to T inverse AT or A is equal to T lambda T inverse, where lambda is a diagonal matrix with the eigenvalues of A on its diagonal. Using the Jordan form of A by lemma 8.5c, we can write any function f of A as t times f of lambda times t inverse. And by lemma 8.5f, we can write f of lambda as the diagonal matrix, which has the entries f of lambda 1, f of lambda 2, and so on up to f of lambda n as its diagonal entries. Now, since all of these f of lambda I are actually scalar functions and therefore well defined, they are straightforward to compute, and hence it's straightforward to compute f of A by just taking t times this matrix times t inverse. So let's look at two examples of computing the square root of a matrix A and the sign of a matrix A for the given matrix A here. At this point, an important word of caution is in order. Namely, you should, under all circumstances, avoid the misunderstanding that the square root of A is just given by taking the square root of each of the elements of A. And similarly, the sign of A is not given by just taking the sign of each of the elements of the matrix A. So I cannot emphasize this enough that you should definitely avoid this misunderstanding. Instead, the square root of A and the sign of A are calculated as follows. We first need to obtain the Jordan form of A by calculating the eigenvalues of A and the eigenvectors of A, where the result is shown here for the given matrix A. Now, for the square root of A, we take the square root of the diagonal matrix lambda, which we obtain by just taking the square root of each diagonal element. So this is equal to the diagonal matrix with the entries square root of 1 and square root of 3 on the diagonal. Then we obtain the square root of A by multiplying the square root of lambda on the left with t and on the right with t inverse, the result of which is shown here. And I leave it up to you to check that with this result for the square root of A, the matrix product square root of A times square root of A indeed yields the matrix A as it would be desired. Whereas if you took the wrong approach by taking the square root of each of the elements of A, this property here would not be satisfied. And it's a good idea to check this for yourself. For the sign of the matrix A, we take the sign of the matrix lambda, which is just defined as the scalar sign of the diagonal elements of lambda. So it's the diagonal matrix consisting of the elements sine of 1 and sine of 3. Then we obtain the sign of the matrix A by multiplying the sign of lambda on the left with t and on the right with t inverse. And if we do that, this is the result that we get for the sign of A. Again, notice that this sign of A looks very different from just taking the sign of each of the individual values of A, which would be the wrong approach. Next, we look at case 2, where the matrix A is not simple. Compared to the simple case of the Jordan form in lemma 8.5, note that in the general case, we must be able to evaluate the function f of j for Jordan subblocks j, which have the form as shown here. So we don't have just a diagonal matrix, but we have also ones on the superdiagonal. As it turns out, the evaluation of a function f of these Jordan subblocks has this general form shown down here, involving the derivatives of f from the derivative of the first order up to the derivative of the order k-1. So unlike f of a diagonal Jordan subblock, which yields again a diagonal matrix, if we take f of a Jordan subblock which has ones on the superdiagonal, we end up with f of j as an upper triangular matrix, where we have f of lambda on the diagonal as before, but now we have the first derivative of f multiplied with 1 over 1 factorial on the superdiagonal. On the superdiagonal, we have 1 divided by 2 factorial of the second derivative of f, and so on up to 1 over k-1 factorial times the k-1th derivative of f of lambda. In the following, we won't be dealing much with the special case where A is not simple, and hence the Jordan form is not diagonal, and we have to apply this formula to compute the function of this non-simple matrix. The reason is that the special case where A is not simple does not provide any additional insights and just makes matters more complicated. However, it is of course important to be able to calculate functions also of non-simple matrices by using the given formula down here. Also, if you're interested, it's not a bad idea to think about where this formula comes from, and let me give you a little hint to this end, namely try to evaluate increasing powers of the non-simple Jordan subblock up here. So compute j squared, j to the 3, j to the 4, and so on, and take a closer look at the results that you are getting. 2 final remarks about computing matrix functions. First, take a moment to verify for yourself that all required function values f of lambda and derivatives fk of lambda are well defined and exist. And second, note that all of this enables us to compute arbitrary analytic functions of any square matrices. This brings us to Theorem 8.6, another central result of this course, which is also called the Spectral Mapping Theorem. In this theorem, let A be a square matrix and f of s be an analytic function whose convergence radius is greater than the spectral radius of A. Then two statements hold. First, if lambda 1 through lambda n are the eigenvalues of A, then f of lambda 1 through f of lambda n are the eigenvalues of f of A. And second, if lambda is an eigenvalue of A with associated eigenvector v, then v is also an eigenvector of f of A associated with the eigenvalue f of lambda in the spectrum of f of A. For the proof of Theorem 8.6, we constrain ourselves to the case where the matrix A is simple. In this case, we have already covered all of the required ingredients, so all we need to do is collect them here again in one place, and this will be a short proof. Since A is simple, by Theorem 7.7, it has a diagonal Jordan form. In other words, there exist two matrices, T and lambda, in Cn by n, such that we can write A as T times lambda times T inverse, where lambda is a diagonal matrix which has all the eigenvalues of A on its diagonal. Here all the other elements of the matrix are of course 0. Now by lemma 8.5 C and F, we can write f of A as T times f of lambda times T inverse, where f of lambda is given as the diagonal matrix with the diagonal entries f of lambda 1, f of lambda 2, and so on up to f of lambda n. Observe that with these two formulas, we have actually obtained a Jordan form for f of A with the eigenvalues being f of lambda 1, f of lambda 2, and so on up to f of lambda n, namely the diagonal entries of the matrix f of lambda, and the same transformation matrix T here and here as for the matrix A. And since the transformation matrix contains the eigenvectors of f of A, this means that f of A and A have the same eigenvectors. And this completes our proof. Definition 8.7 defines the resolvent of a matrix A, which will be of great importance when we talk about continuous time state space models in the next chapter. And the resolvent is in fact a function f, which maps from the complex plane except the eigenvalues of A into the space of n by n matrices, and it's defined by f of s is equal to Si minus A inverse. Recall that this notation stands for set subtraction, so we're actually subtracting all the eigenvalues of A from the complex plane. As we shall see in just a moment, this is necessary for this inverse here to exist. In other words, this inverse exists, or the resolvent of A is well defined for all values of S in C except at the eigenvalues of A. By remembering fact 213, the resolvent can be expressed as 1 over the determinant of Si minus A times the adjugate matrix of Si minus A, which is equal to 1 over the characteristic polynomial of A times the adjugate matrix of Si minus A. So let's look at a quick example where we want to compute the resolvent of this given matrix A. It follows that Si minus A is given by having S on the diagonal and subtracting all the entries of A. And therefore, the determinant of Si minus A can be computed as the product of these two elements minus the product of these two elements, which can be simplified to the polynomial s squared minus 5s plus 7. Moreover, the adjugate matrix of Si minus A is given by this matrix, which is the transpose of the cofactor matrix, and the cofactor matrix consists of the corresponding minors of the matrix Si minus A. For instance, the minor of the element 1, 1 is the element 2, 2, so S minus 3, and the minor of the element 2, 2 is the element 1, 1, so S minus 2, and the other two elements turn out to be 1 and minus 1. If you're not familiar with how to compute the adjugate matrix, please go back to the corresponding slide in chapter 2. With these two results, we can actually conclude that the resolvent of A, Si minus A inverse, is given by 1 over s squared plus 5s plus 7 times the adjugate matrix of A. Again, I recommend to check that this matrix is indeed the inverse of Si minus A, which is given up here. Before we continue, I would like you to observe that every entry of the adjugate matrix is a polynomial of degree 1, which is naturally the case by the very construction of the adjugate matrix using the minors of the matrix Si minus A. And since A is a 2 by 2 matrix, the maximum order of polynomials that will appear in the adjugate matrix is order 1. If A were a 3 by 3 matrix, the minors would lead to polynomials of a maximum order of 2. If A were a 4 by 4 matrix, a maximum order of 3, and so on. So generally, we can say that since each entry of the adjugate matrix of Si minus A is a polynomial of order n minus 1, or we should say of at most the order n minus 1 in S, the resolvent can also be written as 1 over the characteristic polynomial of A times some appropriate matrices Kn minus 1, Kn minus 2, and so on down to K1 and K0, which multiply the corresponding powers of S. So Kn minus 1 multiplies S to the n minus 1, Kn minus 2 multiplies S to the n minus 2, and so on, up to K1 multiplying S and K0 multiplying S to the 0. Let's go back and take a quick look at what this means for our little example for our 2 by 2 matrix A, where we have computed the resolvent by this expression. Now we can obviously split this matrix into two terms, one corresponding to the first power of S and one being constant. So here this matrix would be K1 and this matrix would be K0. Based on this, we have lemma 8.8 stating that the matrices Kn-1, Kn-2, and so on down to K0 of the resolvent satisfy a given set of recurrence conditions. These recurrence conditions involve the coefficients alpha n-1 down to alpha 1 and alpha 0 of the characteristic polynomial of A, and they look as follows. First, Kn-1 is identity, and then there's a recurrence condition for kn minus 2 in terms of kn minus 1, which we have already computed, and the coefficient alpha n minus 1. And this condition reads as kn minus 2 minus kn minus 1a equals alpha n minus 1 times identity. And in the same way, we can continue to compute kn minus k minus 1 from kn minus k via the corresponding recurrence relationship involving the coefficient alpha n minus k, down to the last recurrence relationship, which reads as minus k naught times a equals to alpha naught times identity. For the proof of lemma 8.8, we start with the definition of the matrices kn minus 1, kn minus 2, and so on down to k0, which are defined as the matrices multiplying the corresponding powers of s, so s to the n minus 1, s to the n minus 2, and so on, down to s and the factor 1, and then times 1 over the characteristic polynomial of a. This is equal to the resolvent si minus a inverse of a. Now we multiply both sides of this equation with si minus a in brackets times the characteristic polynomial chi a of s. Then on the left hand side, the inverse of si minus a multiplied with si minus a yields the identity matrix, and on the right hand side we can cancel the expression for the characteristic polynomial chi a of s. Therefore, we obtain that the identity multiplied with the characteristic polynomial is equal to this polynomial in s times si minus a, where we can now substitute the characteristic polynomial on the left hand side, and we can multiply these two brackets on the right hand side and combine the same powers of s together, yielding this coefficient for the nth power of s and this coefficient for the n minus 1th power of s, and so on, down to this coefficient for the first power of s and this coefficient for the constant. Now the result is immediate by comparing the coefficients of all different powers of s on both sides of the equation. So for example, for the nth power of s, we get that identity is equal to kn minus 1. For the n minus 1th power of s, we get that alpha n minus 1i is equal to kn minus 2 minus kn minus 1a, and so on. Note that by virtue of lemma 8.8, we can now compute the resolvent of a by using the given formulas instead of going through the complicated process of computing the adjugate matrix of Si minus A. In fact, Si minus A inverse can be computed by the following algorithm in n steps. We start with kn minus 1 equals to identity, then we solve the second equation for kn minus 2, which is equal to kn minus 1a plus alpha n minus 1 times identity. And then we go on in this fashion by always computing a k with an index that's by 1 lower than the index that we had before, and by using this formula down to k0 times a, which equals to minus alpha naught times identity. And then the resolvent of a, Si minus A inverse, is given by 1 over the characteristic polynomial of a times all of these factors that we have just computed multiplied with the corresponding power of s. Now we are really close to another cornerstone of linear algebra, the Cayley-Hamilton theorem. To this end, we first need to define what's called an annihilating polynomial of a matrix A. So let A be a square matrix, then some polynomial p of s is called an annihilating polynomial of A if p of A equals to 0. With this definition, the statement of the Cayley-Hamilton theorem is actually quite simple. It says that any square matrix A satisfies its own characteristic polynomial. Or, in other words, the characteristic polynomial of A, chi A of s, is an annihilating polynomial of A in the sense that chi A of A equals to the zero matrix. At this point, it should be emphasized that the Cayley-Hamilton theorem is an extremely powerful theorem that we will use a lot in the rest of this course. Given the work we have already done for lemma 8.8, the proof of the Cayley-Hamilton theorem becomes actually fairly short and simple. Starting with the formula k naught a equals to minus alpha naught I, we substitute the formulas of lemma 8.8 recursively. So in the first step, for k naught equal to k1a plus alpha 1I substituted for k naught here yields k1a squared plus alpha 1a is equal to minus alpha naught times identity. Here we can bring the term alpha 1a to the right hand side, and then we substitute the next formula, which states that k1 is equal to k2a plus alpha 2I, which, when substituted for k1 into here, yields k2 times a to the power 3 plus alpha 2 times a to the power 2 is equal to minus alpha naught times identity minus alpha 1 times a. Again, we can bring the second term on the left-hand side over to the right-hand side. And now we can already see where this is going. So if we continue like this, up to kn minus 2 is equal to kn minus 1a plus alpha n minus 1I, then we obtain the equation kn minus 1 times a to the n is equal to minus alpha naught times I minus alpha 1 times a, and so on, up to minus alpha n minus 1 times a to the n minus 1. Finally, with the last condition that kn minus 1 is equal to identity, we can substitute identity at this point here and bring a to the n to the other side of the equation to obtain that 0 is equal to minus alpha naught times I minus alpha 1 times a minus, and so on, up to minus alpha n minus 1 times a to the n minus 1 minus a to the n. Observe that the right-hand side of this equation is exactly equal to minus the characteristic polynomial chi a of the matrix A. And since on the left-hand side we have a 0, our proof is complete. On the last slide of this chapter, we have stated some properties of the matrix exponential in lemma 8.11. The matrix exponential is the scalar exponential function, which is an analytic function applied to square matrices. It assumes a central role in the theory of linear systems, and we will use it a lot as we go along. Now, when we go through the list of properties of the matrix exponential, you will recognize that actually many of these properties are analogous to the properties of the scalar exponential. So for instance, in part A, it's stated that e to the a times 0 is equal to identity. This would be equivalent to the scalar case where e to the 0 is equal to 1. Then in B, we have that e to the a times t plus s, where t plus s are two scalars. This is equal to e to the at times e to the as, again analogous to the scalar case. C is a little different to the scalar case. Only if we have two matrices A and B which commute, only then it's true that e to the a plus bt is equal to e to the at times e to the bt, which is again equal to e to the bt times e to the at. D, e to the at in brackets adjoint is equal to e to the adjoint of a times t. E to the at is non-singular for all scalars t, and moreover, the inverse of e to the at is equal to e to the minus at. F, the determinant of e to the at is equal to e to the trace of at. G is the part where it really gets interesting with respect to linear systems, namely x of t defined as e to the at is the unique solution to the system of ordinary differential equations given by d dt of x of t is equal to a times x of t, with the initial value of x naught being equal to the identity. And somewhat similarly, h, x of t being defined as e to the a times t minus t naught for any t naught in R is the unique solution to the system of ordinary differential equations d dt x of t is equal to a times x of t, with x of t naught being equal to identity. Throughout the proof of lemma 8.11, we will restrict ourselves to the case where A is actually a simple matrix. Non-simple matrices, as before, just make matters more complicated without providing any additional insights. Then the matrix exponential function, or simply the matrix exponential, is defined as we would expect from our considerations of matrix functions. So since A is simple, by theorem 7.7 it has a diagonal Jordan form, which looks like this, and by the definition of a matrix function, namely f of A is defined as t times f of lambda t inverse, where f of lambda is just given as the scalar function of the corresponding eigenvalues of A, is now given particularly for the exponential function as e to the a, which is defined as t times e to the lambda times t inverse, where e to the lambda is simply the diagonal matrix that results by taking the exponential function of all of the eigenvalues lambda 1 through lambda n. This makes the proof of part A almost self-explanatory. Since A times 0 is equal to the 0 matrix, this 0 matrix has the Jordan form T times 0 matrix times T inverse, because all the eigenvalues of the 0 matrix are 0, hence we get a 0 diagonal matrix, and therefore it follows that e to the a0 is equal to e to the 0 is equal to t times the diagonal matrix, where we have e to the 0 for all diagonal elements times t inverse. But this matrix here is of course equal to identity, and then it follows that this is equal to t times t inverse, which is again identity. For the proof of part B, first note that for the multiplication of a matrix A with a scalar t, a corresponding Jordan form can be obtained by just multiplying the matrix lambda with the scalar t. So we have the same transformation matrices T and T inverse for the Jordan form of AT, and instead of the diagonal matrix with the eigenvalues lambda 1 through lambda n of A, we now have the diagonal matrix of lambda 1 times t, lambda 2 times t, and so on down to lambda n times t. Therefore, we can write e to the a times t plus s, where t plus s is just another scalar, as t times this diagonal matrix, where we now have the scalar exponentials of e to the lambda 1 times t plus s down to e to the lambda n times t plus s, and then times t inverse. On the other hand, we have that e to the at times e to the as is equal to t times the diagonal matrix of e to the lambda 1t through e to the lambda nt times t inverse. So this is e to the at, and then times t times the diagonal matrix of e to the lambda 1s through e to the lambda ns times t inverse. So this here is equal to e to the as. Now clearly t inverse times t in the middle here yields identity. And then if we multiply these two diagonal matrices, we get another diagonal matrix whose first entry is e to the lambda 1t times e to the lambda 1s. And since now we have a scalar exponential function, this is equal to e to the lambda 1 times t plus s. And we can do the same thing for the rest of the diagonal elements. So what we get is t times this diagonal matrix times t inverse, which is exactly equal to e to the a times t plus s. The proofs of parts C and D are omitted, as they are pretty straightforward and not very interesting. Part E is immediate with part C, and part F is left for you to solve as part of exercise sheet 8. For part G, it holds that with the Jordan form of AT being equal to this type of expression where we just multiply the diagonal matrix lambda with the scalar t, so each of the eigenvalues is multiplied with t, and hence the matrix exponential e to the at is equal to t times e to the lambda 1t, e to the lambda 2t, and so on the diagonal down to e to the lambda nt, and then this matrix is multiplied also with t inverse. Therefore, when taking the derivative ddt of e to the at, the matrix t and the matrix t inverse are just constants, and what we need to do is take the scalar derivatives of each of the diagonal entries of this matrix here, which is easy to do because it's just lambda 1 times e to the lambda 1t, lambda 2 times e to the lambda 2t, and so on down to lambda n times e to the lambda nt. Next, observe that this diagonal matrix can be written as the product of two diagonal matrices, namely lambda and e to the lambda t. So with this, what we get is t times lambda times e to the lambda t times t inverse, where we can now insert a t inverse t in the middle between lambda and e to the lambda t, because this expression is just equal to an identity matrix. But now notice that the first three expressions here are exactly equal to a, and the second three expressions are equal to e to the at. So we have proved that e to the at satisfies that d dt e to the at is equal to a times e to the at, which is exactly what we wanted to show, and together with the fact that e to the a0 is equal to identity by part A of this lemma, the proof of part G is complete. For part H, we first observe that by part B of this lemma, e to the a times t minus t0 can be written as e to the minus a times t0 times e to the at, where this first matrix, e to the minus a times t0, is constant in t. Then by part G, it follows that d dt of e to the a times t minus t0, for which we can substitute this expression. And this first matrix is constant in t, so we can pull it to the front, which yields e to the minus a t0 times d dt of e to the at, and this by part G is given by a times e to the at. So this whole thing is equal to a times e to the minus at0 times e to the at, where the last two factors can be combined into e to the a times t minus t0. And finally, to complete the proof of part H, we observe that by part A, we have that e to the a times t minus t0 is equal to identity when we substitute t0 for t. So this completes our proof of lemma 8.11.